My name is Carlos Prado. Thank you for your attendance to this training session. And I'm going to talk about how to understand and how to interpret climate scenarios to be used for studies about forest fires. The presentation is divided into 3 parts. In the first part of the presentation, I will be talking about how to interpret this climate model data for fire management. After that, I will be introducing some useful tools to analyze this data. And the last part will be a practical exercise where you will see how to download and manipulate all this climate data. Okay, we're going now to the first part of the presentation, how to interpret climate data for fire management. Well, the main thing in climate models is that we have to distinguish between meteorological data and climate data. Meteorological data describes a current situation. Today is sunny, it's rainy, it's windy. And if we translate this to fire management, this meteorological data lead us to take immediate decisions. And these immediate decisions can be used to fight forest fires. For example, well, wind now is coming from north, and in 3 hours it's changing to south. All this information is useful for firefighting in this moment. This is completely different to climate data. Climate data represents an average condition in some area. For example, average temperature in Italy is 20 degrees, but in 50 years it will be 23, for example. Climate data cannot be used to take immediate decisions. Must be used to take long-term decisions. If we translate this to forest fire management, this climate data can be used for planification and adaptation into future climate conditions to fight forest fires in a better conditions. Okay, a very important thing when we work with climate models is the concept of downscaling. When you extract data from a climate model, it has a resolution of 100 kilometers. You can see this figure when you see that, for example, the Sardinia island is divided into 4 tiles. This is not representative to the climate of all the island. What we have to do, downscale this information to information that is really representative of the area that we have to analyze. How can we do that? We use observations, historical meteorological observations, models of reanalysis, satellite data, and now is getting more and more important, machine learning models. With all these tools, we translate this information with a resolution of 100 kilometers to a resolution of 1 kilometer. Why is this important? Because it allow us to identify microclimates, local winds, ecological effects in areas with high mountains, or distribution of vegetable species. And all these facts are absolutely important for fighting a wildfire. That is why we work with very local information. Well, the first step to start working with climate projections is to obtain downscale projections for critical variables for wildfires. For example, some of the climate variables that can be important for a forest fire could be temperature, relative humidity, rainfall, wind speed and wind gusts, and radiation. This is an example of a project that we had in Andalusia region in Spain, where we calculated all this variable information and see the evolution in the future. I don't know if it can be seen well. This is the average between 2041 and 2070, and 2071 and 2100. So here we can see the evolution in the future of the climate variable that you want. These are different scenarios. We will introduce later the concept of climate scenario, but it's very important to make averaged projections in future climate periods to work with climate data. Combining the previous variables, temperature, precipitation, and humidity, and other variables, we can obtain much more specific variables for analyzing the risk of fire. For example, drought indexes like drought code, SPI, or aridity indexes, bioclimatic indexes to see how vegetable species are going to evolve, evapotranspiration, that it's very important for the water stress of the plant, and we can also obtain wildfire indexes like the FWY. And we can work as well with thresholds, for example, to calculate a number of days of a heat wave, a number of days with temperature above 40 degrees, things like this. In this figure, we have an example about a fair weather index calculation in the metropolitan area of Barcelona in Spain. And we can see the average evolution between June and September of the index along different climate periods. So this information is also very useful to obtain fire risks for the future using the climate projections. And another important information that we can obtain is the distribution of vegetable species. We have previously calculated the bioclimatic indexes, and by using these bioclimatic indexes can be can be launched models that evaluate future changes in vegetable distribution. Coming back to Andalusia region, this is the distribution of the Pinus sylvestris between 1985 and 2014. And these distribution models show us that in the future, climate conditions are not going to be good for the development of these species. This is important because imagine that we have an area where the unique vegetable species is Pinus sylvestris. We see this information and we say, okay, by 2100, in the worst scenario, we don't have to worry about forest fire because this will be a desert. This type of vegetation is not going to exist at this time. So this can be very useful as well to evaluate the risk of fire. And the final objective is to obtain an index of vulnerability or forest danger. For example, this is I think the FWY for Copernicus, the website of Copernicus, but this is meteorological. So the objective with climate models is obtain this information, but for future scenarios. How is going to change the risk of fire in different areas? Well, we are going to talk now about climate scenarios. The first thing is to distinguish as well between weather models and climate models. Weather models predict very short ranges, short or medium ranges from today until 15 days. And these models are updated every 6 hours, are updating continuously. And the output of these models are called forecast or prediction. Climate models predict for a very long range, daily projections from 2015 to 2100, and these models are updated once in a decade. For example, the last version is called CMIP6, that was developed between 2013 and 2020. And this output is not called forecast, it's called projection, ¿vale? Climate projections.
Vale.
It's very important that we have to work with 30-year averages to have a representative period. And we have to work as well with moving averages. We don't have to work with day-by-day data. For example, is it useful to take serious that the 1st of January of 2064 is going to be 20 degrees? No, we don't have to take this data. We have to take averages. We are going to explain now briefly the concept of climate model. A climate model is a very complex integration of a lot of environmental variables used for understand our climate. Now, climate models are very sophisticated and they are called Earth system models because they take into account all this information: atmosphere variables, land, ocean, and the dynamic of ice in the surface. So all these models process this information, and with the equations of atmospheric working, they make the projections. These climate models are combined with the scenarios. The scenarios are called Shared Social Pathways, SSPs. The SSPs take into account a lot of socioeconomic variables, such as population, land use, technology development, pollutant emissions. And we have 5 SSPs right now. SSP1 is called sustainability. This is like an ideal world where all the energy is going to be clean, a lot of adaptation measures and mitigation, and the rest of SSPs consider the different levels of population growth, economic growth, use of fossil fuels, and the most catastrophic one is the SSP5, which is called fossil fuel development. And these SSPs are combined with RCPs, which is the CO2 emissions. For example, SSP1 is combined with a RCP of 26 geotons per year of CO2. The SSP2 is combined with 45 gigatons emissions, SSP3 with 70, and SSP5 with 85. So these are the most important scenarios: SSP 126, 245, 370, I5, and 585. So we have the SSPs combined with the RCPs, the emission scenarios. This information is combined with the equations that the model uses to interpret the climate, and the output is the climate data. We have a lot of models. We used to work with these 10 models. This is a small sample of models. These models, as we have seen before, has 4 SSPs. So we have in total 40 combinations of projections between model and SSP. Why is this important? Because we have a lot of uncertainty. When we work with climate data, is key to interpret the uncertainty. How can we interpret this uncertainty? We have some examples here. For example, for a single point, we can use plumes or box plot, where we can see the evolution of a variable under each scenario. This is a temperature plume, where in every color is a scenario, and the range of uncertainty are the 10 models. For example, in the SSP 585, we have models that project a temperature increment of 5 degrees, and we have models that project increments of 7.5 degrees. And we can translate this information into box plot to see how different models have different outputs. And we can interpret this uncertainty spatially. Coming back to Andalusia again, here we can see the 4 scenarios, 126, 245, 370, and 585 in 2 periods, 4170 and 7100. And we can see spatially which areas can be more affected by the changes. Well, once we have introduced scenarios, we have an important question to ask. Taking into account these different climate scenarios, how would affect these changes to fire management? I am not a fire expert, but I have some ideas about how can answer this question. For example, in almost every projection, we are seeing that the summer is expanding to adjacent months. This is an example about days with average temperature between 17 and 25 degrees in Huelva, Spain. And here we can see that under the scenario, this is a 5. This is 585. Current conditions. So these years on the top are between 2015 and 2020. So current conditions in summer are going to be in maybe May, June, September, October in 2100. That is this year here. And we are also seeing in a lot of projections that summer conditions which involve high danger to fire risk are expanding to northern areas of Europe. So, taking this into account, what we are saying as well, unusual events. And it's very important to study if these now unusual events, if they are going to be normal in the future. For example, in October on 2017, we have a fire event in Spain and Portugal driven by Hurricane Ophelia, which provoked very, very strong winds from south, from Africa, very dry and strong winds. And there were devastating forest fires in Portugal and northern Spain. And the California wildfires, now in January 2025, where the Santa Ana winds combined with a very unusual drought leading to these devastating wildfires that we all have seen 1 month ago. So it's very important to concentrate in study the recurrence in the future of these unusual events to see if these conditions are going to be more frequent. Taking this into account, I can ask myself, does it make sense to maintain the concept of summer campaign? We have seen that Hurricane Ophelia was in October. The California wildfires have been in January. Summer conditions are expanding into spring and autumn. So does it make sense to keep on working just concentration efforts on summer? So Right now, these efforts are concentrated in summer, but they are increasingly occurring at unusual times of the year. And these have a lot of dimensions. For example, public administration. Are they prepared to allocate resources, both human and financial, even in winter? And as a social dimension, are we aware that some of the cautions and prohibitions that now suffer in summer, for example, barbecues or things like that, are we aware that we are going to have to prevent these forest fires for the rest of the year? Well, these questions can be answered interpreting climate data. Well, we'll move on now to part 2, practical tools for working with all this data. First of all, in the framework of FirEUrisk, we have generated a climate data repository, which is on this link. We will be diving into this link afterwards. We have generated information of 10 variables: maximum temperature, minimum temperature, maximum humidity, relative humidity, minimum relative humidity, total precipitation, wind speed, components U and V of wind, and radiation, both long wave and short wave. This is, if you go into this website, you have two parts of the repository: information of 90 kilometers and downscaling 1 kilometer. In the downscaling 9 kilometer, you can find information available for a grid covering of whole Europe. From 32 to 72 degrees north of latitude and from 15 degrees west to 35 degrees east of latitude. In downscaling 1 kilometer, we can find only information for the 5 pilot cases and 25 demonstration areas, adding the special case of Sardinia and Corsica. In the grid of whole Europe, we have 32 combinations model a scenario. We have downscaled 8 models with their corresponding 4 SSPs. And we also have historical data and reanalysis, the ERA 5 lands. As this information, these files are very space consuming, we have downscaled only 3 combinations, model a scenario for 1 kilometer. These 32 combinations have been ordered by future changes of drought code, and we have taken only 3 combinations of these 32. These 3 combinations are representative of scenarios with low climate change, scenarios of average climate change, and scenarios of very high climate change. So with these 3 combinations, we have covered a very big range of uncertainty of climate change projections. Well, this is the data repository that MeteoGrid has generated just for FirEurisk. But if you want to work with raw data of other models, in everything is centralized in the website of Copernicus. To access to this data, you have to register in this website, and you have a lot of data about atmosphere, marine, land, etc. Some of the data are free, and some of the data you need a license, and the download could be in the website interface or through the API. But this is just if you want to download by yourself the climate data directly from the models. Well, this is an example of how you can download this data from these models. The most useful thing is to do a script for the API, taking into account the temporal resolution that you want, the scenario, variable, pressure level, and these data are automatically downloaded. Well, now we're going to talk about some tools for data manipulation. For data manipulation, normally we have, well, the most important programming languages are R and Python. R is more oriented to statistical analysis and data visualization. The best environment for using R is RStudio. And Python is more powerful for developing artificial intelligence and machine learning models, with the best environments are PyCharm and Jupyter. And right now, R and Python are very easily interchangeable. There are libraries in both languages that can easily adapt one language to another, and even you can use in these environments, you can use some tools that allow you to program one part of the script in one language and another part of the script in another language. For example, if you want to develop a machine learning model, you can do a part in Python, and if you want to analyze the data that you obtain, you can use R. I use normally R, and in this session, the training, we are going to use R and RStudio. If you want to work with these tools, you can go to this link to download and install. The climate data files are usually we have two main formats. First of all, we can work with GeoTIFF, which is a type of file that can be viewed in a tool called QGIS. And if you want to handle GeoTIFF files in R, raster and Terra are the most important libraries. And well, if you want to work with an interface, one of the best are QGIS. Here in QGIS can open a file and add different layers, polygons, lines, shapes, contours. We can change geographical projections. You can export layers. You can cut an area and export. Well, QGIS is a very powerful tool to work with climate data. And the most common format for climate data is netcdf. The extension is .nc. Well, netcdf is the acronym for Network Common Data Form. And the main advantage is that you can store a lot of variables in the same file. It's a multidimensional file. This file is structured into 4 parts: variables that are stored as a multidimensional arrays. We can store as well time series or matrices. We have the dimensions that represents the physical dimensions, for example, longitude, latitude, time, or height. And the attributes provide information about all these variables and dimensions, for example, units or type of calendar. And the conventions, that is the name that they give to the global metadata. One powerful tool to view netcdf files is Panoply. Panoply can be downloaded and installed in this link. And if you view a file in Panoply, it has these aspects. Longitude, latitude, time are the dimensions, and tmax is the variable. And inside the file, you have the description of the dimensions, the number of steps of longitude, number of steps of latitude, numbers of steps of time, the variables, unit, description, and the metadata, grid, area covered, etc. And the file, when you plot it in Panoply, has this aspect. And it's very useful, this tool, because you can add here counters, change the grid, change the plot labels, projection. Okay. And to handle netcdf files in R, it's advisable to use ncdf4 and Terra, but the difference is that Terra extracts the information as a raster layer, and ncdf4 extracts the data as an array, as a matrix. So depending on how you can manage the data, you can use either of them. But I think that the most important tool to manage climate data is called CDO. CDO is the acronym for Climate Data Operator, and is a collection of more than 700 command line operators to manipulate netcdf files. It has a lot of strengths. It's very fast, consume very low computational resources, and it's very intuitive to use it. To download and install is this link. It's available for all these operative systems, and I recommend you to save in your favorite files this one, because it's a complete, a full user guide of CDO. The general structure of the operator of CDO is, if you use the command line in Linux, you have to put CDO, the operator, and the file that you want to change. If you have an input and output, you have to write CDO the operator, and after that the file the file of the input and the file of the output. And if you are going to do operation that requires more than one input file, the structure is this one. This we will see some examples. So, okay, if you want to use CDO in RStudio, you have to put this information inside the command system. This is which we are going to use in the training, okay? The most used commands in CDO are averages. For example, if you have a file with daily data, these commands are used to...
No, perché qui stanno rispondendo.
Sorry?
Scusa, I'm sorry, Okay. They closed the mic. Sorry, Carlos.
Okay. Well, these are the name of the commands used to do averages. We can do year averages, month, daily average. And this is the structure to do these averages. Alternatively to the averages, we can calculate extremes. For example, the operator for a yearly average is year AVG. So if we want to calculate maximums of the year, we have to write year max or year min or mon max, mon min. These all these commands are for extremes. We can also do operations with a constant. For example, if we have to change a file which is in Kelvin to Celsius, we have to write this CDO subtract the amount that we want to subtract, input file, output file. We can do operations between two data sets. For example, calculating change increment between two climate periods. So we write CDO subtract input file 1 is one period, input file 2 is another period, out file is the difference between them. We have selection commands. For example, we can select time, hour, day, months, year. Imagine that we want to select data from 2015 to 2020. This is the command. CDO, cell year, write the years between commas, input file, output file. If we want to select just an area, CDO, cell lot lamp box, we write the longitudes and latitudes, first longitude, then latitude, input file, output file. We can select variables, and this is a little bit more complex. We can merge files. For example, if we have two variables, we can put it in the same file, and we can apply an expression to an input file. We can see this better with an example. We want to obtain wind speed from wind components U and V. The first step is to merge the files into just one file containing the two variables U and V. This would be the command cdo merge time file with the component U, file with the component V, and the out file which will contain U and V together. And the second step is to apply the expression to calculate wind speed, which is this square root of the component's square component. So the command would be cdo expr, and here we write the expression. We put here the variables, the name of the variables, which is not the same as the name of the file. Here the name of the files are out file U and V, but the name of the variables are U10M and V10M. And we obtain the output file, which is the wind speed. And okay, the last part of this training is a hand-on exercise about downloading data and manipulation. And I've divided this exercise into two parts. The first one is a basic script in R to download data from the FirEurisk data store that we have in Meteogrid. The demonstration area that I have chosen is the A5IT, which is the island of Sardinia. And well, for this, I'm going to RStudio. If you go to the link, this is how information is structured in the data store. So if you go to the case of Sardinia, is this one. Data is structured into 3 folders: Era 5 Land, Future, and Historical. And each folder have information about the climate variables and well, this is for future, this is historical. And what are we going to do? We are going to download the data for this case study for future and historical. For the variables, I think no. Okay, we are downloading the most critical variables for evaluating risk fire: maximum temperature, minimum relative humidity, total precipitation, and wind speed. Okay, you can download data file by file. If you define here the root, you define here the parameters. This is the area. What scenario do you want? Medium, future period, Tmax, and if you run this small part of the script, download just one file, takes about 20 seconds, and it's download here, this one. Now we open it with Panoply, and as we can see, everything that I explained before, we can see the information about the variable, about the dimensions, and if we plot, we obtain all this information here, and we can change here wherever you want. You can change the overlays, you can change the grid to 1 degree. I encourage you to use all this information once we finish the session, because can be very useful. And in this script, the second part of the script is used to download the data that you want for a case study. For example, I've downloaded these 4 variables: maximum temperature, minimum relative humidity, precipitation, and wind speed for Sardinia, for these scenarios, lower, medium, and upper, and for the 2 periods, future and historical. So if you copy, well, I think that you will have this script. So if you change the paths, you can use it to download the information to your own computer. Okay, so well, if you run this function, you obtain 24 files, about 64 gigabytes in 1 minute. But I have parallelized a function with 12 workers. You have to see the number of workers that you have on your computer. I'm working through a server, so I have 24 workers. So I put 12. So I've downloaded all this information in 1 minute. If you use just one worker, you probably get this information in about 12 minutes. So, well, take into account that the files are very heavy, 64 gigabytes in total. So make sure that you have enough space in your memory to store this data. Well, if you run this part of the file, you obtain a folder. So you basically replicate the folder that you have in the repository with the number of variables that you download to your computer. Here is the information that we have downloaded in 1 minute. And now we are using this information that we have downloaded to analyze this data with CDO. And this is the next part of the exercise. According to the data that we have just downloaded, in this exercise, we are going to try to answer this question. Which areas of Sardinia would increase their vulnerability by the end of the century, respect the reference period in summer months? We are going to analyze the data that we have downloaded to try to answer which areas of Sardinia will be more vulnerable to forest fires. So with this, we will put in practice everything that we have talked about before. Well, if you go to R, you have another script. I'm going to share this script. I'm going to share these scripts with you, and changing the paths, you will work with them in your computers with no problem. Well, we need historical data from 1985 to 2014. First of all, with the package Terra, we open this data. This is historical data. And as we are using Terra, the data is represented by a spatial raster. And we see here in time that we have the correct dates that we need from 1985 to 2015. To answer this question, we need future data from 2071 to 2100. So we open this data, and we can see here that we have data from 2015 to 2100. Here we don't have data from 2015 to 2070. So, which is the first step? Get the data from this file only to 2071 to 2100. If you remember the CDO commands, there is one of them called CDO cell year. Around here, to time selection, we have to select only the years that we are interested in. What we do to achieve it, we choose all the files that we need. We put the years that we are interested in, separated by commas, from 2071 to 2100. We define the path of the output, and we apply the CDO commands over all the files. To do this, we do a loop. We do a loop with all the files. So we have a folder here. In exercise 2, where we have, for example, relative humidity. If we open this, we now have data only from 2071 to 2100. Well, once we have the data of the periods that we want, the next step is to select the summer months. We want data only for summer months. We use the command cellmonth. We have defined here this command cellmonth, and the command would be cdo cellmonth 6, 7, and 8 input file, output file. Here we do 2 loops. First one for historical data, second one for future data. On this loop, we have applied with the command system. We have defined, first of all, the input file, secondly, the output file, and if we launch this command, we obtain data only for summer months. Okay. Once we only have summer days, we calculate the average of the whole period, because right now we have here, after applying the cellmonth operator, here we have data only for June, July, and August for 2071 to 2100, but we have daily data. Remember that we cannot work with the data day by day. We have to do the average. So we are now doing the average of this 2,760 days. Remember in the presentation that to do the average, we used these operators. We want the average of a whole period, so we have to use the operator team average. So now in the script, to calculate this average, use this cdo command, cdo team average in file, out file, and we do the same. First for historical data, in a loop for all the files, then for future data, in a loop for all the files, and we obtain the average data, which is here, a team average. And now if you open one file, you will see that you have just one time step. We have calculated the average of all the time, and the aspect is like this. Okay, so once we have average data for future and average data for past, we are going to subtract to calculate the difference between future and past. To do this, we use this operator. We want to do the arithmetic between two datasets, dataset of future, dataset of past. So we use the command sub to subtract. So if we go to the script, this is the CDO command that we have to launch. CDO sub in file 1, that is the future, in file 2, that is the information of the past, and the out file. Define in files, define the out file, put the CDO command, and we obtain the difference here in change. Here, this is the change for all the scenarios, for all the variables. If we open this, this is the change of temperature between future and past. And now to summarize this information, we have done here some figures, and the results of these figures I will show you in the presentation again. Okay, we have done all the calculations, so let's see if we can answer this question. All the files that we have obtained are these ones. These are the results for maximum temperature under lower, medium, and upper scenarios. We can see that along all the island of Sardinia, temperature change would be between 2 and 7 degrees. These are the results for relative humidity. We can see that is going to decrease about between 2 and 5% on average. These are the results for precipitation that is going to remain fairly unchanged. And these are the results for wind speeds that, well, will remain fairly unchanged under the upper scenario. It's going to decrease, but very slightly, about 0.2 kilometers per hour. So these are the results that we have commented right now: increase in temperature, decrease in humidity, some decrease in precipitation and wind speed. Which conclusions can we obtain from this? That the changes in temperature and humidity would lead to worsen critical indices for forest fires. If you have more temperature and less humidity, you are going to increase evapotranspiration and water stress. So risk danger is going to increase as well. And these worsening conditions would be more significant in inland areas. For example, temperature increases are higher in inland, lower in coasts, and in humidity results are fairly the same. So the summary is that with a very, very simple script, we have come to the conclusion that we can obtain good results to analyze future climate change in Sardinia, and accordingly, these results can extrapolate to assess fire risk. And for me, well, is enough for now. Thank you for your attention, and well, looking forward to your question. Thank you very much.